Hello everyone, good afternoon, very good afternoon to one and all. Students, can you able to hear my voice? Am I visible and audible? Good afternoon, Tejaswini, good afternoon. Students, can you able to hear my voice? All of you? Can you able to see my screen? Yes? Fine. So let's start with the today's session. So before moving on to today's class, let's recall the yesterday's class, okay? So let's keep the recall session as a recall test for today. And I'm going to ask you 3 questions, okay? So the first question is, what is the relationship between E naught cell and KEQ? What is the relationship between E naught cell and KEQ? Can anyone give me the answer in the chat box for this question? Yesterday we have discussed Nernst equation and the relationship between E naught cell and KEQ and Faraday's first law and second law, right? So from that, you give me the relationship between E naught cell and KEQ. What is KEQ? First of all, it is an equilibrium constant, right? So what is the formula we have studied under this? I need a formula. You need the formula. Try for the formula. One of you give me the answer in the chat box. None of you remember the relationship between E naught cell and KEQ? What happened? I need the formula. It's very easy, no? E naught cell is equal to E naught cell is equal to E naught cell is equal to 0.059 divided by N into log KEQ. Okay, please don't forget. Please don't forget. So the second question is Faraday's first law formula. So this is very easy compared to the first question, right? So at least give me the answer for the second question and the third question. First, go with the second question and give me the formula for Faraday's first law. What is the formula for Faraday's first law? Very good. W is equal to Z into I into T. Very good, Tejaswini. This Tejaswini, no? Yeah. Yeah. Z into I into T, my dear Golab. It is not Y, okay? It is T. But anyway, I think it is your typographical mistake. Fine. Then where Z is the equivalent with over there, okay? And we will be finding out the thing over there. And then coming to the Faraday's second law formula, it is W1 divided by W2 is equal to E1 by E2. Okay, so these are the 3 formulas which we have discussed, and along with this, we have studied one important formula which is from Nernst equation. Got it? And today we are going to continue with one problem from Faraday's second law, and then we are going to enter into the new topics for today. Okay? So the question is this. A certain current liberated 0.504 gram of hydrogen in 2 hours. How many grams of copper can be liberated by the same current flowing for the same time in a copper sulfate solution? So what we have to do? We have to go with the Faraday's second law of electrolysis. Okay? And the law or the equation or the formula which the second law says is that W1 by W2 is equal to E1 by E2. So where 1 is the hydrogen and 2 is the copper. Okay, 1 is the hydrogen and 2 is the copper. Got it? So we are asked to find out the grams of copper. We are asked to find out the grams of copper. Means the weight of copper we have to find out. Okay, and we are provided with all the 3 values, remaining 3 values. So we have to calculate the equivalent weight of this copper. So to find out the equivalent weight of copper, we have one formula. Yesterday we have studied that, and that formula is atomic mass divided by valence. Okay, and the atomic mass of copper is 63.5 and the valency of copper is 2. So mostly copper in copper sulfate solution, it exists in 2 plus form, right? So the value of copper is 2. Valency of copper is 2. And if we divide these two, we will get 31.75 gram per equivalent, okay? And the equivalent weight of hydrogen is, atomic mass of hydrogen is 1 and the valency of hydrogen is also 1. So 1 by 1 is equal to 1. So we have EH2 and ECU. And then we have to go for the mass of hydrogen. Mass of hydrogen is already given in the question, right? It is the mass of hydrogen. So 0.504 gram is the mass of hydrogen. So substitute all the values. So if you substitute, you will get 0.504 divided by WCU is equal to 1 divided by 31.75. So take this W weight of copper to the other side and bring everything to this side. So you have to multiply, no? You have to multiply 0.504 into 31.75. Can anyone multiply and give me the answer? Can anyone give me the answer? So try to multiply fast and let me know the answer in the chat box. One of you do it fast and give me the answer in the chat box. What is the amount of copper? How many grams of copper can be liberated? Very good, Mahir. Very good. 16.002. 16.0. Very good, Tejaswini. I hope you guys are doing everything on your own. Okay. You guys are not using the calculator, right? Don't use calculator. I hope. I think you guys are doing one very good, Mahit, and very good Tejaswini. The answer is 16.002. Okay. So all of you can able to understand how to apply the formula of second law of electrolysis to the numericals, right? Do any of you have any doubt or do any of you feel it difficult in applying the terms or in applying the given values here? E represents the equivalent weight, okay, where it has to be found out from atomic mass divided by valency formula, and W is the mass, okay. We are provided with the mass of hydrogen and we are asked to find out the mass of copper. So how many grams of copper means it denotes the mass of copper, and that's what we have got it from this question. Is this question clear to all of you? Do any of you have any doubts? Any doubts from this? So only by solving more number of questions like this, you will get the practice over this and you can able to solve any type of question which are asked in the exam. Okay. So I hope this is clear to all of you. No doubt, right? We can move on to the next slide now. Say yes or no. Yes. Okay. So coming to today's session, the learning objectives for today's session is mainly about the conductivity of electrolytic solution. Okay. So in that we are going to study about the products of electrolysis, conductivity cell, measurement of conductivity and cold rush. So coming to the products of electrolysis, so just look into the picture. We have the electrolytic cell. So yesterday we have discussed about the cell, no? So we have a beaker and two electrodes are dipped into that. One is a cathode and the other one is the anode. And it has been connected to the battery, and we have the cations and anions in the solution. Okay. So cations are moving towards one electrode and anions are moving towards the other electrode. Okay. This is the electrolytic cell setup. And the products of electrolysis depends upon the state of electrolyte. Electrolyte means that electrolytic solution. Okay. And the secondly depends upon the electrode which we are using, that is cathode and anode. And thirdly, it depends on the concentration of the electrolyte. Concentration means the strength, whether it is more concentrated or it is more diluted. So the products of electrolysis depends upon these three terms: the state of electrolyte, and the electrode, and the concentration of the electrolyte. Okay. Now let's see one example. Let's see the electrolysis of molten NaCl. Let's see the electrolysis of molten NaCl. So I have taken the molten NaCl in a beaker, and I have dipped two electrodes inside that, where one is the platinum anode and the other one is the platinum metal cathode. And it has been connected to the DC source. And since molten NaCl is present inside the container as electrolyte, it has Na plus and Cl minus ions. So all the anions are moving towards the left side anode, and cations are moving towards the cathode. Okay, anions will always move towards the anode because anode is a positively charged electrode and cathode is a negatively charged electrode. So all the cations will move towards cathode, plus will move towards minus, and all the minus will move towards plus. Okay. So now at anode, what happens? At anode, what happens? So who is moving towards the anode? Cl minus is moving towards the anode. So when Cl minus, when the aqueous Cl minus moves towards the anode, so it is getting converted to half Cl2 with the release of one electron. So when two Cl minus combines together, they form a Cl2 molecule and they are giving out one of its electrons. So this is what is happening at anode. And at cathode, what happens? Sodium is moving towards cathode, no? So this is the cathode, and sodium ions are moving towards this cathode. So in cathode, at cathode what happens? Reduction happens. At anode what happens? Oxidation occurs at anode. So the minus one charge is getting converted to 0. And at cathode, reduction occurs. So sodium will gain one electron and it will be converted to sodium. So the plus 1 is getting converted to 0, means it is reduction. Okay. Now the products of this particular electrolysis is chlorine is deposited at anode and sodium is deposited at cathode. So these two are the products. Chlorine is deposited at the anode in the form of gas. Sodium is deposited in the form of solid. Clear for all of you? Do you have any doubt from this? So these two, chlorine and sodium, are the products of this electrolysis of molten NaCl. Clear? Shall we move on to one more example? Shall we go with the electrolysis of aqueous NaCl? Yes, right? Hi, Sakshi. Good afternoon. Yeah. Electrolysis of aqueous NaCl. So in aqueous NaCl, if you see, we have a beaker again, and aqueous NaCl is present inside the container as electrolyte. Okay, and again platinum anode, platinum cathodes are platinum anode and platinum cathodes are dipped inside the electrolytic aqueous NaCl solution, which has been connected to the DC source. Okay. So in aqueous solution, we do have H2O molecule. In aqueous NaCl, we do have, in molten NaCl, we have only NaCl in the molten state. But in case of aqueous, we also have H2O, right, inside the solution. So we will have H plus ion as well as OH minus ions. Got it? So we have Na plus, H plus and Cl minus ions in the solution. Okay, now at anode, what happens? Oxidation occurs again at anode. So again the Cl minus is converted to Cl2 with the release of one electron. Then the E naught value associated with this particular reaction is plus 1.36 volt. Okay, and also we have H2O, right? So the two H2O molecules which is present there in the liquid form, it is getting converted to the oxygen gas, and 4 hydrogen ions are coming out from that and 4 electrons are coming out. And the E naught value associated for this particular reaction is plus 1.23 volt. So now the reaction at anode with lower value of E naught is preferred. So these two reactions can occur at anode. So there are two possibilities. Two reactions can occur at anode, but the one with the lower value of E naught is preferred as a to form as a product. Okay, so who is having the lower value of E naught? It is obviously H2O, right? So that particular reactor will occur at anode. So that is preferred. Got it? So next coming to, here we have one order. So here you see, CF minus is lesser than SO2 2 minus and NO3 minus, OH minus, Cl minus, Br minus and I minus. So this is the tendency. This is the order in which the product is forming. Okay. Now coming to cathode. So in cathode reduction occurs, as usual, sodium will gain one electron and it will be converted to sodium. E naught value is minus 2.71. And coming to H plus. H plus also gains one electron and it is getting converted to hydrogen ion in the cathode. The E naught value for that is 0 volt. Okay, now the reaction at cathode with a higher value of E naught is preferred. So which reaction? Higher value means the positive value. So H plus electron giving half H2 reaction is preferred over this. Okay. So what is happening? The second reaction is occurring here. Second reaction is occurring here. And the products of electrolysis are chlorine at anode and hydrogen at cathode. Okay. Chlorine at anode and hydrogen at cathode. So there is some mistake here with the E naught value. Okay, there is a mistake here in the E naught value. So let me just look into that and then I will rectify. Okay. So because the one with the lower value of E naught is preferred for anode reaction. Got it? So chlorine Cl minus reaction should have the lowest value. And that is the product which is formed at anode. Only there is some mistake with this E naught value. I will check that and let you know in the next slide. Okay. Fine. So at anode we have chlorine and at cathode we have hydrogen. So these two are the products of the electrolysis of aqueous NaCl. So students, this is clear for all of you? Except this part. Can you all able to understand? So which is preferred over the one for all? Yeah. Fine. So with this, the products of electrolysis part is getting over. Now, next we are moving on to the conductivity of the electrolytic solution. Conductivity of the electrolytic solution. Okay. Good evening, students. Good evening, GOP. Is GOP a single student? What is the name of full name of GOP? Okay. Okay. Is your name G? What is your name? From JNV Anand. What is your name? Okay, okay, okay. Good evening, Dhanushree. Good evening. So, students, whenever you join the Zoom, try to join from your name, okay? So that I can call your name, no? If it is GOP, it is something different, right? So, okay, good evening, Dhanushree. So, try to join the class on time, okay? It is already 3:24, you see. You have missed few things, but anyway, no issues. You can go through the videos in the YouTube, but try to join on time and follow the class. Very good. Very good, Dhanushree. Thank you so much. Yeah, let's go with the conductivity of electrolytic solution. So before moving on to the conductivity of electrolytic solution, we should know what is a conductivity cell first of all. Okay, what is a conductivity cell? So to understand this, I am going to take a system with the, which having the electrolytic solution present inside this, and the platinized electrodes are dipped inside them. Okay, platinized electrodes are present inside that particular cell, and the cell is called as conductivity cell. And in this conductivity cell, the R, which is called as resistance, is proportional to L by A. It is proportional to L by A. Okay, if I remove that proportionality symbol, I have to introduce a constant rho. So if I write a letter like this, it is called as rho. Okay, and it is a Greek letter which is called as rho, which is called resistivity or specific resistance. Rho is called as specific resistance or resistivity. And the SI unit of this rho is ohm meter. In terms of centimeter, it is ohm centimeter. Okay. And the inverse of resistance is called as conductance. Conductance is denoted by the letter G. Since it is the inverse of resistance, I can write G equal to 1 by R because it is the inverse, no? So G is equal to 1 by R and the SI unit of conductance is Siemens. Siemens is denoted by the letter S or ohm inverse. Conductance is denoted by ohm inverse, or you can call this ohm inverse as mho. Ohm inverse means just revert this OHM to MHO. So you get mho. Okay. So since it is the inverse, conductance is the inverse of resistance, you have to just reverse it. Ohm inverse, or you can call it as mho. Clear? Clear, students? So there is L means the length of the wire, and so here you can see no the length between the two electrodes, and A is the area of cross section. Got it? Yes. So take down this formula. This formula is very, very important. R is equal to rho into L by A, and G is equal to the reciprocal of R. Unit is very important again. Unit of rho is ohm meter, and the unit of R is ohm, and the unit of conductance is mho. Okay. So don't forget, don't get confused. So write and keep everything neatly and clearly. Okay. So shall I move on to the next slide? Have you noted the all the points which is there on the screen? Yes. Okay. The okay, students. Now let's see the factors affecting the conductance of electrolytic solution. Okay. Factors affecting the conductance. Conductance of electrolytic solution can be affected by the nature of electrolyte. Secondly, it is affected by the nature of solvent. Thirdly, it is affected by the size of ions. Fourth, it is by concentration of electrolyte. And the fifth, it is affected by the temperature. Okay. So all five factors are very, very important. So what are the factors which affects the conductance? Nature of the electrolyte, nature of the solvent, size of the ions, concentration of electrolyte, and temperature. Okay. For example, I am going to take NaCl. So NaCl can be dissociated into Na plus and Cl minus. And if it is like this, then it is called as complete dissociation. Okay. And I'm going to take one more compound as an example, which is ammonium chloride. And the formula is NH4Cl. So NH4Cl can also be dissociated into NH4 plus and Cl minus. But the reactants and products are in equilibrium with each other. Means it has undergone only partial dissociation. It has undergone only partial dissociation. Got it? Now here if you see to the NaCl, so in NaCl what we have? So you see here the ionic mobility, the movement of ion is getting less. So between the three container, if you observe, in the first measuring cylinder, if you see, the particle is coming down quickly, and in the second measuring cylinder, it is coming a little bit slow. In the third container, it is coming down very, very slow. So what is the meaning of this? The ionic mobility. Mobility means the movement. The movement of ion is getting very slow from beaker 1 to beaker 2 to beaker 3. So why it is like this? What is the reason behind this? What is the reason behind this? Means it is due to the third factor, which is because of the size of the ions. It is because of the size of the ions. Okay. And it is, if the size of the ion is very, very small, what will happen to the ionic mobility? If the size is very small, it will come down easily, no? So ionic, on moving down the group, the size of the ion increases and the ionic mobility decreases. Ionic mobility decreases. Yeah, very good. So the small sized people or the small atom or the small thing can move very fast compared to the bigger size atom, no? So it is the case with the ions also. So here you see we have a very small lithium ion. So many water molecule can come and form the bond with this lithium ion. And many are surrounded. So it can be hydrated so easily. Since it is having the very least size, it can move here and there so easily and can form the bond with many water molecules. Okay, so the conductance will be very high. And coming to the concentration of the electrolyte, if the concentration is more, then the number of ions is more. Okay. And if I draw the conductance versus concentration graph, I will get a linear line. Means if I increase the concentration, conductance is also high. So that is the meaning for this linear graph with a positive slope. Got it? So if the concentration is 3 molar and if the concentration is 2 molar, then a solution with 3 molar concentration will have more number of ions, and the conductivity of that 3 molar solution will be more. Got it? So directly proportional. Concentration is directly proportional to the conductance. Got it? Now last, coming to the temperature. If I increase the temperature, kinetic energy will also increase. Why it will increase? Kinetic energy is called as half mv square. Half mv square. So, if I increase the temperature, the mass and the velocity will increase for that particular substance. So, because of this, kinetic energy will increase. If the kinetic energy of a species is increasing, then the movement of that particular ion will also increase. Okay, clear? It will also increase. So because of this, if I draw the conductance versus temperature graph, if I increase the temperature, then the conductance is also slightly increasing from the lower value to the higher. Conductance is increasing on increasing the temperature. Got it? It is not having a straight line like in case of previous case. It is increasing slowly. It is increasing. Conductance is increasing slowly. Got it? So students, can you able to understand all the 5 factors which affects the conductance? The first is the nature of the electrolyte. For strong electrolytes, complete dissociation occurs. If complete dissociation occurs, the number of ions produced is more. Okay, so they will conduct more. Got it? So this is upon depends on the nature of the electrolyte. Then coming to the nature of the solvent, ionic mobility differs. Then coming to the size of the ion, if small sized ion have the more ionic mobility, so it can conduct more. And if the concept coming to the concentration, if the concentration is more, conductance is more because the number of ions produced is more. Then coming to kinetic energy, yeah, okay, my dear, I will explain. Tanushree, I will explain. See, if you increase the temperature, what will happen? Let me show this with a diagram. Okay, so I'm taking a beaker. Okay, and I have some solvent and some solute particles are there. Salt is there. Okay, and if I increase the temperature of this system, what will happen to these particles? So they will try to move here and there. No, if I increase the temperature, what they will do? They will move here and there. So the velocity is increasing. Mass can be fixed for that particular electrolyte, for that particular compound, but the velocity, the speed will increase if I increase the temperature. So half mv square is nothing but the kinetic energy. So if this velocity term is increasing, then obviously kinetic energy will increase, no? So this is increasing because of the movement of this ions. Since the ions are moving very fast, velocity is more, kinetic energy is more. So on increasing the temperature, conductance will also increase. So they are maintaining a straight line kind of curve. Okay, it is increasing, but slightly it is increasing, and then gradually it is increasing and then going to a constant value. Clear? So conductance is directly proportional to temperature, and conductance is directly proportional to concentration. Okay, conductance is inversely proportional to the size of uh, the ion, size of the ion. Yeah, I will come to the nature of solvent. I will come to the nature of, if the solvent is different, so solvent can be anything, no? Solvent can be water, or the solvent can be ether, or the solvent can be benzene. So this, if I take, for example, if I take sodium chloride, okay? So I have a sodium ion over there. The sodium ion movement in benzene will be differing from water, and it will differ from ether. So since the three solvents in the which is present in the three measuring cylinders are different, the movement is different for all the three. The ion can be same, but the movement is different. Mobility is different because of the nature of the solvent. So some solvent can bring down the ion easily, so quickly, to the bottom part. Some can bring them very slowly only. Okay. So it depends on many factors again. So is that clear, Vaishnavi? Nature of the solvent. Solvent cannot be water all the time. Okay. It can be different solvents also. Okay. Fine. Yeah. Now coming to the conductivity cell. Okay, students. Great, you guys are asking me questions. I'm so grateful to answer those questions for you guys. I hope you guys are listening, and I'm very happy. Okay, because you guys are listening very, what to say, very keenly. Fine. So let's go with the conductivity cell. So here is the conductivity cell, okay, in which we have a tube kind of thing, and electrolytic solution is present inside the tube, and it is connected to a platinized anode and platinized cathode. Okay, and they are being connected to the DC source and ampere, etc., etc. Now, as we have already seen, the conductance is the inverse of resistance. Conductance is the inverse of resistance. Now, we know that R is equal to, what is R? R is equal to rho into L by A. So, in place of R, you substitute this value. So, if we substitute R is equal to rho L by A, we will get this. Rho into L, divided denominator of the denominator, we go to the numerator, and we will get an expression like this. Okay. And here you see, we have the platinized anode and the platinized cathode. We have the platinized anode and platinized cathode. So now the inverse of this, what to say, this rho, inverse of rho is called as, inverse of resistivity is called as kappa. This is called as kappa, and it is the conductivity. Rho means resistivity and kappa means conductivity. Platinized means platinum metal, you all know, right? So we have a rod with an electrode, and that electrode is being coated by a platinum metal, so which is called as platinized cathode and anode. So it has been coated with a platinum metal. That electrode is coated with a platinum metal. Okay, clear? Is it clear for Dhanushree? Yes. Okay. Yeah, the 1 by rho, 1 by that is the inverse of resistivity is called as conductivity, and the SI unit of conductivity is Siemens per meter. Siemens per meter. Okay. And also we have one more relation. L by A is equal to the length of the rod, length between the rod and the area of the cross section. That L by A ratio is called as G star, which is called as cell constant. G star is called as cell constant, and the SI unit of cell constant is meter inverse. And if I substitute L by A is equal to G star in this particular equation. Here I have A by L. L by A means it is inverse. So it is 1 by G star and 1 by rho is called as kappa. Okay, it is called as kappa. Got it? It is a Greek term again which is called as kappa. Actually, it is denoted by like this. Okay. So in place of 1 by rho, you can substitute kappa, and in place of A by L, we can substitute 1 by G star, and we are getting one final relation from this conductivity set. Got it? K is equal to, yeah, K, kappa is equal to G into G star. Very good, student. Very good. Kappa is equal to G into G star. Okay, good. So students, do any of you have any doubt from this slide? So again, we have few formulas here. I will tell you the important formulas. Just note down those things. So the important formulas are the last formula, and this 1 by rho is equal to kappa. Everything which I am teaching you is very important only. Okay, the very most important thing I am mentioning here. And the unit is very important. You should know the term for each letter. Suppose if I am giving rho, then you should know it is resistivity or specific resistance. And if I put kappa like this, then it means conductivity. If it is A means area of cross section. If it is G, it is conductance. If it is G star, it is cell constant. Okay, if it is R, it is resistance. So you should know the term for each letter. Got it? Clear for all of you? So first of all, make sure you are thorough with all the terminologies and the letters and the symbols. Got it? Clear. Got it. Very good. So now let's go with the classification of substances on the basis of conductivity. Okay, so we do have many substances on the basis of conductivity. Those substances do have different names. Okay, so a substance can be classified into conductor, okay, insulator, and a semiconductor. So based on the conductivity values, based on the conductance, it has been divided into three like this. Okay. So which substances are called as conductor? So the conductors are the substances whose conductivity means kappa value, whose kappa value is greater than 10 power 4 Siemens per meter. Okay, if the conductivity is greater than 10 power 4 Siemens per meter, then that particular substance is called as a conductor. So examples are sodium metal, copper metal, silver metal, and gold metal. Okay, and what about insulator? Insulator means just the opposite of conductor. Kappa value will be less than 10 power minus 10 Siemens per meter. Kappa is lesser, but lesser than 10 power minus 10 Siemens per meter. Okay, examples are glasses and Teflon. Teflon, you all know, right? Have you ever seen Teflon? It is there in your home itself. Did you guys see Teflon in your home? Yes? No? So we do have pans, no? We do have pans in our homes, no? For frying purpose. We do have pans, right? So there is some black colored thing coated on the pan, no? So that is called as a Teflon. And it is a polymer. It is a polymer, which is called as Teflon. Clear? Now you all of you have seen, no? In your home. Yeah. Glass and Teflon are the insulators. They do not conduct much. They do not conduct the electricity much. Okay. Yeah, next coming to semiconductor. So semiconductor conductivity values ranging from 10 power minus 7 to 10 power 4. 10 to the power minus 7 to 10 to the power 4. So these values are very, very important. All of you have to make a note of it. Okay. So if it is greater than 10 power 4, it is a conductor. If it is less than 10 to the power minus 10, it is insulator. And if the conductivity value is between 10 to the power minus 7 and 10 to the power plus 4, then it is called as a Semiconductor. Examples for semiconductors are silicon, germanium, and copper oxide. Very good, Sakshi. Very good. Examples for semiconductors are silicon, germanium, and copper oxide. Okay. And apart from this, we do have superconductors. Have you heard of this term superconductors ever before? Any of you? Do any of you have heard of this superconductor? Yes. What is superconductor? Can you give me the definition for superconductors? No. Dhanushri has heard of this superconductors term, I think. So can Dhanushri give me the definition? Okay. What is the definition for superconductors, my dear students? No resistance to the electric current. Very good. The superconductors are the substances which have zero resistivity or infinite conductivity. It has zero resistivity or infinite conductivity. Okay. We cannot say no resistance. Yeah. We can also say like this. Okay, just when you're good. So zero resistivity or infinite conductivity having substances are called as superconductors. Metals and alloys at a very, very low temperature are the examples for this. 0 to 15 Kelvin. Okay, very low temperature it is, no? Yeah, it is called the zirconium, zinc. So these are the elements on the metals, alloys, which are called as superconductors. Okay, and ceramic materials also will come here. Ceramic materials and mixed oxides also show superconductivity even at 150 Kelvin. Okay, so C60 CS2RB is one compound. HgBa2Ca2Cu3 OX is another compound, which is called as HbCCO. Okay, so there are some examples for superconductors substances. Got it? So this is about the classification. Now we'll do one problem based on this concept which we have discussed. Okay. So here is the question. Kappa is equal to conductivity of 1 by 50 normal KCl at 298 Kelvin is 0.001765 Siemens centimeter inverse. And the resistance of cell containing this solution is 100 ohm. Calculate the cell constant. What is cell constant? It is G. So we are asked to find out the G value. How to find out the G value? We have studied one formula, right? G is equal to kappa divided by G star. What is G star? Kappa by G. Okay. So it is kappa by, I'm sorry, G star is cell constant. No, G star is cell constant. So now we have to find out G star. So I'm sorry, student. G star is cell constant. So that we have to find out G star. G is conductance. So resistance. So to find out this G star, we need kappa and G. We need kappa and G. We are not provided with the G value. What is G actually? G is the conductance. We are not provided with the conductance value in the question. But we can take the conductance from the resistance using this inverse formula. Conductance is the reciprocal of the resistance. Okay. So in place of 1 by G, so here we have 1 by G, no, in place of this 1 by G, you can put R. If you put R, what you will get? G star is equal to kappa into R. So what is the value of kappa given in the question? Kappa is conductivity. Conductivity of this particular cell is 0.001765. Okay. Into resistance. Resistance is also given. Resistance is 100 ohm. So multiply these two numbers and find out the answer. So just we need to move the decimal to the right side. So we will get 0.1765. So we have to move here 1 and 2. Okay. Since it is 100, 0.1765 centimeter inverse is the value for cell constant. Is it clear to all of you? So you need to know how to take out the values from the question, and you need to find out the term which is being asked in the question, and then think of the formula which has to be applied. So, okay, if it is cell constant means, so we have studied one formula. So, what is that formula? And just recall. Okay, and go to the terms which are present in that formula. So, here in this formula, what are the terms we have? We have G, kappa, and G star. So, we are asked to find out this G star, and the remaining two terms which we need to know is G and kappa. So, where G is the conductance, without knowing that G is a conductance, you will not be able to solve this question. Okay, so that's why I told you to study all the terminologies which is being mentioned for each letter. Okay, without knowing G is a conductance, will you be able to solve this question? Somewhat difficult, no? So, firstly, that is important. You should know what is G and what is kappa. G is conductance and kappa is conductivity. So conductivity is given in the question, but conductance is not given. So we can go, but resistance value is given in the question. So what I can do, I can take the inverse and then I can substitute and get the answer. Okay, so this is how you have to approach each and every physical chemistry question. Okay, so question which has numericals like this. So otherwise, you will feel this type of lesson as a very difficult lesson. Okay, but actually, this type of lessons are very easy. So nothing to study much. Only the formulas we have to study. Okay, we need to identify each and every term. That's all. You will get to solve this type of question very easily by practice. But daily you have to sit and practice. Daily you have to solve at least one question from each lesson. Okay, clear for all of you? So do any of you have any doubts so far? Clear. Okay. So the next thing is measurement of conductivity. So the next is measurement of conductivity. So how we are going to measure the conductivity using an instrument, okay? So here we have an instrument which is called as Wheatstone bridge. Okay, you might have heard of this Wheatstone bridge in which we have four resistance value R1, R2, R3, R4, and we have a conductivity cell at R2 position, and we have a variable resistance which is called as R1, and P is the detector. Whenever detector shows no current, then we can say R1 by R3 is equal to R2 by R4. Okay. R1 by R3 is equal to R2 by R4. So what is R2 from here? So bring this R4 to the other side. Okay. You will get R1 by R3 into R4. Okay. So this is the formula to find out the resistance or the conductivity, cell resistance. Okay. So we know that conductivity is equal to kappa and it is equal to G into G star, and G is equal to the inverse of resistance. If I have to find out G2, then it is 1 by R2. So in place of G, substitute 1 by R2. So you will get 1 by R2 into G star. So which is again the another relation to find out the conductivity from the resistance. Okay. So these two formulas are very, very important. And from these two values only, conductivity measurements are made for the corresponding cells. Clear? So the next topic is molar conductivity. So that we can discuss in the next session. Okay, we'll discuss it on Sunday. Clear? So tomorrow is holiday for you, so we will discuss it on Sunday. So today we have discussed many topics. We have recalled the Nernst equation, Faraday's laws, etc., etc., and then we have discussed about the factors affecting the conductance and some informations about the conductance we have studied, and we have studied about the conductivity cells also. And before these three, we have studied the products of electrolysis part also. Okay, which is the last topic from yesterday's session. So we will continue the molar conductivity tomorrow, and after completing that, we'll go with the Kohlrausch law. So is that okay for all of you? We'll complete Kohlrausch law, and After that, we will try to solve some problems from the topics which we have discussed so far. Okay? So is it okay for all of you? So do any of you have any doubts from today's session? Okay. Okay then. Thank you, students. Thank you so much for listening. Take care. Bye-bye. See you all in the next session. Okay, no doubts. Yeah, bye-bye. Bye.